Welcome to the Laboratory of Evolutionary Computation. Over 1 billion years, creatures in nature have evolved to solve a large variety of problems, from giraffes who use their necks to reach the tallest leaves, to colorful flowers that attract bees, from bioluminescent fishes deep under the ocean, to spiders with their complex webs. Through evolution, nature found creative solutions to many types of complex problems. What if we could use the power of evolution to solve problems in human society as well? Let us create many different computer problems to solve some engineering problem. For example, to create a new car. Some of these computer-generated cars will be fast, others slow, some safe, others dangerous. Using natural selection, we keep the best cars and cross over their computer genes. Mutations will bring new ideas into our population. We repeat this process again and again, and after many generations, evolution will produce a new car design that is fast, safe, and unique. This process is called evolutionary computation. By replicating the process of evolution artificially, we can have computers automatically find solutions to hard problems with minimal human input. In the Laboratory of Evolutionary Computation, we research how to use this research to solve unique problems in our society. Let me introduce some of the research topics in our laboratory. Master student Wu Zitong uses evolutionary computation to design soft robots. Soft robots are composed of flexible cubes. They can adopt several body configurations to solve tasks such as search and rescue in hostile environments. Using evolutionary computation, Wu aims to develop the bodies and controllers of soft robots interactively in a virtual environment, using the process of selection, crossover, and mutation. In this way, the robots can evolve to perform tasks such as walking, crawling, and jumping under difficult environment conditions. For a problem closer to our day-to-day lives, PhD student Guilherme Nakahata is working on the optimization of schedules for bus drivers. Guilherme uses evolutionary algorithms to find ways to allocate bus drivers to intercity routes in a way that is smart and efficient. However, what if a driver becomes sick in the morning? This is the problem of uncertainty. The key insight of this research is how to deal with uncertainty to generate robust solutions to problems. To minimize the effects of uncertainty, this research uses a technique called landscape analysis. Landscape analysis extracts the characteristics of an optimization problem and analyzes them using computer algorithms. Using landscape analysis, we can predict and minimize the level of uncertainty in the solutions found by the program. Master student Hiroto Abe is also researching how to use evolutionary computation to improve public transportation. His research topic is the dial-a-ride problem, or DARP. DARP is used in the real world in a demand-responsive transport systems. Imagine that you could request a transportation from point A to point B, and the vehicle would pick up not just you, but other passengers that want to be transported to similar locations. DARP can be more flexible than bus services, but also more efficient and environmentally friendly than taxis. Research on DARP tech requires solving a complex optimization problem that involves multiple objectives and constraints. In this project, we use multi-objective evolutionary computation to compare the trade-offs of different solutions and find routes that balance passenger expectations, vehicle efficiency, and road congestion. A different way we can use evolutionary computation for social sustainability is through multi-agent simulations. These simulations replicate complex situations in society. Then, using virtual agents, we can see how the situation develops in different scenarios. For example, master student Yusen Du is researching the simulation of macroeconomics. His research constructs a virtual stock market with agents representing investors and government agents. How would the economy react to policies such as changing the interest rate? In this scenario, evolutionary computation is used to make the agents act intelligently, as well as to find the best policies for certain market targets. Simulations can also be used to represent specific events. Master student Tanjina Sarif Karim studies the movement of crowds during the Hajj, the annual pilgrimage to Mecca, and one of the world's largest human gatherings. In this research, we simulate the Tawaf, where pilgrims circle the Kaaba in the Mataf area. By using a simulation, we can understand what happens as the space becomes more crowded, where congestion begins, and what can be done to keep everyone safe. Pilgrims are represented by agents who move, interact, and respond to different stimulus. Using evolutionary computation, we can design and test new strategies for efficient crowd management, making the pilgrimage experience safer and more meaningful for millions of people. Finally, we can use simulations to speculate about the past. PhD student Sara Satake is developing an agent simulation of early societies, where agents represent hunter-gatherer hominids who must learn about the environment and support each other to thrive. The focus of this research is to model reactive communication, where agents learn to leave clues for each other in the environments, and to recognize these clues so that they can understand where the food is and where it is dangerous to explore. By understanding this decentralized mechanism of communication, this research aims to uncover how simple and local mechanisms can scale into collective patterns of coordination and meaning-making. Eventually, this work seeks to generate insights into the origins of language. Evolutionary computation can also be used to give us more insight into the nature of computers themselves. Gwenole Moisson, master student, is researching the evolution of cellular automata. Cellular automata are mathematical models that can be used to identify emergent behavior. Lenya is a cellular automata based on the game of life and aims to replicate lifelike processes in the continuous domain. Past research showed that the game of life can replicate key characteristics of computing systems. Using evolutionary computation, we are looking for the same property in Lenya. If we can find the building blocks of computing inside the Lenya model, we could be one step closer to tie the connection between computers and life. The evolution of mathematical models is not only useful for computational theory, but it also has computer industry applications. Felipe Nonato, a PhD student, is researching how to use the evolution of computational models to automatically generate video game content. This research aims to understand how to generate content that is diverse and functional. Inspired by the capabilities of evolutionary processes, this research aims to generate games that are as diverse as the natural world itself. These are just some of the ideas of how to use evolutionary computation for theory and practice. Inspired by nature, we hope to create computing systems that are efficient, creative, and surprising.